So we'll be talking about quantization techniques, and see what kind of trade-offs that you have to deal with when you're trying to run these large language models on edge devices, right? Okay. So let's try to understand why quantization is popular. As you know, there are a lot of popular network compression techniques like knowledge distillation, pruning, quantization, or network architecture search. And each of them has their own advantages. And quantization in particular has been one of the popular techniques because it right out of the bat, you're talking about converting these float point models into int 8 or lower precision. So what that means is you are getting at least 2 or 3 folds of savings in memory, as well as 2 to 3 times improvement in compute efficiency. And this is really important for LLMs. As you can imagine, they're eventually growing in size. And when compared to the GPUs that are expected to run this model, the scaling of memory is not proportional. Here is a graph that shows you how these models, for example, some of these large language models have like hundreds and billions of parameters, and the memory that is available with even the high-end GPUs might not be able to support them. So by just using quantization, you might be able to bring the size of these LLM models to a fraction of what they usually are, with minimal loss in accuracy, so that you should be able to run it on a more moderate device. So it helps you to reduce the model size as well as improve compute efficiency. While it has these advantages, the maintaining the accuracy of these models is still challenging. And that is what we hope to address with some of the techniques that we discuss in today's presentation. So before we dive...
Yeah, that's fine.
That's good. Okay. Yeah. So let's talk about the basics of quantization. So quantization is the process of mapping any float or real value into integer space. What it means is you are essentially trying to, instead of doing float point arithmetic, you can do an integer arithmetic, which means most of the hardware will be able to do it more efficiently. And so when you take a distribution, like any floating point value, you might be able to quantize. And in broadly, the quantization schemes can be divided to 2 types, like symmetric and asymmetric. So when you look at a symmetric distribution, as here, it's surrounding the 0, which means you're able to map without taking into account the 0 point. Whereas in case of an asymmetric distribution, we're talking about a more skewed distribution. And so we are essentially calculating the scale and 0 points for these floating point values to map them onto integer range. And this is essentially a trade-off. That is, we are trying to trade off the precision with the range. And this is really an important point. We will be coming back to this throughout our slides on how we would want to make this addition trade-off. Again, when we are talking about integer representation, it might be 4-bit, 8-bit, or 2-bit. So it's really crucial that we make use of the precision that is available and not waste it on outliers or anything like that. So when we are selecting these min-max values, it's also important to understand the distribution and also make sure that you are getting rid of the outliers. So when it comes to model quantization, again, these can be deep learning models, CNNs, LLMs for that matter. They're essentially broadly classified into 2 approaches. That is quantization-aware training, and the other is the post-training quantization. When it comes to quantization-aware training, that is when you're training the model, you know that you're going to be quantizing it. So you introduce fake quantization nodes into the model. That is essentially allowing the model to learn to adapt to this quantization noise and the error that comes with it. While it's popular and seems to work most of the cases, it is very compute intense, and it adds a lot of compute cost when it comes to that. Whereas in case of post-training quantization, this is more popular because of its nimble nature. That is, you're essentially taking already trained model that's available or that you have already trained, and then trying to quantize it onto your device or the accelerator that you want to run it on. Now, because of its less compute intense nature and an ability to support different quantization schemes, post-training quantization seems like a more popular approach. And in this talk, we'll be talking about some of these techniques like SmoothQuant or activation aware quantization and Llama.cpp, and see how we are able to achieve good performance as well as accuracy with these quantization techniques. So this is one of the popular slides on how a transformer model architecture looks like. And as you can see, it's a repetition of same blocks. And if you look at these building blocks that form the transformer architecture, you can broadly classify these operations into two types. One is the compute intense operations, the operations like matrix multiplication or the linear or the fully connected layers. These are more compute intense operations that contribute to the most of the max or the flops of the transformer network. And we also have normalization, element-wise addition, or the activation layers. These are more memory bound because you're essentially, when you're trying to execute them, you are essentially trying to move a lot of data in and out. So the compute versus bandwidth, they're more compute or memory bound operations when compared to the MATML. So this kind of distinction is important when you are also quantizing, because you want to avoid any overheads due to quantization, which we will discuss in the next coming slides. So here's an overview of the precision mapping for transformer. So when you have a transformer architecture like we discussed the last slide, we see that the compute intense operations are the ones that get the most advantage by using quantization. And whereas the other operations like normalization or activation or element-wise add, if you try to quantize those operations, you might end up seeing much more degradation in accuracy, as well as the quantization might add an extra overhead for the models. So the most popular approach is to quantize and delegate these more compute intense operations like MATML and linear layers onto the accelerators, and use the CPU or another float point processors to do more memory bound operations like the activations and element-wise addition. And another level of granularity is when you are doing quantization, you are essentially trying to map a float point distribution into an integer space. Now, how do you do that? Like in case of a transformer, for example, you can take the whole weight tensor, treat it as one float distribution, and do quantization. For the most cases, it might work well, but depending on the distribution of weights, you might see that some channels have more varied distribution when compared to the others. Now, when you're trying to quantize the whole weight distribution as a single tensor, it is obvious that when we looked at the scale and the offsets, if you are trying to map it to the high variance channel, the other channel might get significantly affected. So much better approach is to have more fine-grained or granular approach. That is, we have per tensor approach, where if you see the distribution is more friendly, you can go for per tensor. And there's per group approach, where you can group, given the vectors for weights and activations, you can group them into smaller chunks, like groups of 64 or something like that, where for each group, you are calculating these quantization parameters, making it more fine-grained. Or you can do per channel or per token. That is more detailed. Again, you are essentially, as you go from per tensor to per channel, you are essentially adding a lot of overheads for quantization. what that means is you are sacrificing performance for precision. So it's always a trade-off between, for example, if you have per tensor, it will be much more efficient than per channel. But if you are not able to get the kind of accuracy that you need, you might want to switch to per tensor.
Can I clarify something?
Sure.
So there's activations, weights.
Yes.
Are both being quantized? Distributions on both, or is it just on weights?
So yeah, we haven't dwelled into distinguishing between active. Oh, sorry. So the question was, we're talking about, we have both weights and activations. So when we talk about quantization techniques and per tensor, are we talking about just the weights or activations or both? I think that's the essence of the question. So right now, we haven't dwelled into how we handle activations and weights because there are definitely different ways to handle that. But for now, in this case, we are just talking about quantization. So either it be weights or activations, it's a float values and a distribution of float values. So at least at this point in the presentation, we don't distinguish between them. But later on, we'll definitely see when we look into the models and how weights and activations differ and what's a better approach for each of them. Yeah. So yes, so we talked about the quantization how approaches in terms of the model as well as different schemes, and we talked about QAT and PTQ methods, and we talked about granularity of quantization. So next, we dive into one of the post-training quantization techniques called SmoothQuant. So here's, I think, where your question is becomes more relevant is we're talking about weights and activations which have their own distributions. So you can always look at the distributions and see which quantization schemes fits better. So for example, you see the weights, and if you see they are more symmetric, you might choose to go with symmetric quantization. And if you look at the weights, if you see a lot of variability across channels, you might think maybe a per channel quantization scheme looks better. But again, the challenge here is if you look at the weights versus activations, you can clearly see that weights, which are we essentially initialized and updated during training process, tend to have much better distribution. So the user also has much better control because they are static. What that means is once you have a trained model, the weights are not going to change. What that means is you have more leverage to look at the weights and have more techniques applied to it. So you have more power to work with the weights. When it comes to activations, they are very much input dependent. This is where it becomes tricky. It can be more, it depends on the kind of input that's given to the network. So what that means is we might see a larger variation. So in this case, this is where we see more conservative approaches for activations when compared to weights. What that means is when you're trying to quantize weights, you understand them better, you know the distribution well ahead of time, and it is static. So it will allow you to do better quantization and better optimization techniques. When it comes to activations, they are more volatile, all are variables. So most of these techniques take a more conservative approach when it comes to activation quantization. Here's an example with SmoothQuant where they show that again, this is an empirical data that shows that weight distributions tend to be more uniform because you're usually initializing the weights with some sort of a normal distribution. So you expect it to be more.
The weight from yes, 3 bar.
So okay. Yeah, I'm trying my best, but yeah, I'll keep up. So yeah, so what the SmoothQuant emphasizes is the fact that activations are more variable, and they came up with a technique where since the weight distribution is more uniform and they know that they can do a better job, they came up with a technique where they can transfer this variability from activations to the weights. So they are essentially talking about adjusting the scales such that at the end of the day, it's like a linear operations where you are multiplying the weights with activations to get the results. You're multiplying the inputs to get the activations. So they kind of essentially do a kind of a smoothing technique where they are transferring this variability from the activations to the weights. What this means is you definitely need a small calibration data set that kind of profiles the variability of activations, and then they have this filter that can migrate this variance from activation to the weights. And this is where they have shown that uh, by using a small so this is what they call it as the migration scale. What it means is that if you have anywhere but between 0 to 1, so again this image shows you a simpler example where you see that the activations have much bigger outliers when you're trying to do quantization. So if you try to quantize just the outlier and try to include it, you will lose precision on the lower distribution. So it's always a trade-off. But if you try to ignore the outlier and include most of the lower distribution, what it means is you might see a significant degradation in the accuracy. So a better way to do it is if we are able to distribute it across weights and activations, it is much easier to quantize. And this is what they call the migration factor. So here's an example of how they do it. Like if you have a 0, that means you keep all the variability within the activations. If it is 1, you're essentially trying to transfer all the variability of the activations into the weights. And with the heuristics, they find that anywhere between 0.4 to 0.5 seems like an ideal candidate. What it means is you're essentially trying to minimize the noise from quantization. So you're essentially trying to distribute the noise across weights and activation equally, and that gives you a better performance. This is also enabling it to use 8-bit quantization for both weights as well as activations. Otherwise, you would probably have to use higher bits for activations and lower bits for weights. But using this technique, they're able to do 8-bit quantization for both weights and activations. And as you can see, this is essentially orthogonal to the quantization schemes that we discussed. That means this is more like a precursor to quantization. This is essentially making the model more friendly to quantization. Once you have applied the SmoothQuant technique, you can either do 8-bit, 4-bit, 2-bit quantization to see how the model performs. So here are some performance and accuracy measurements. I know there are a lot of metrics for LLM performance measurement, and I think that's a different topic in altogether. So here we discuss some basic perplexity measurement on Wiki as well as performance measurements through like latency. And as you can see, they're able to do a reasonable job without much degradation in terms of accuracy. Again, for those uninitiated, perplexity measurement is essentially a measure of how confident the model is when it's predicting the next output. And usually the lower, the better. So we are comparing with FP16 and seeing how the quantized SmoothQuant model with 8-bit quantization for weights and activations performs. And we also see that we see better latency, that is faster response time for some of these OPT models. Now, in the SmoothQuant, we talked about how activations are very volatile and how by distributing this volatility to activations from weights, we can minimize the quantization noise and get better performance, right? So another technique that is quite popular is activation-aware weight quantization. Now, if you think about some of these quantization techniques like pruning, you might the first intuition might be to use the absolute weights. So, for example, in pruning, usually they try to take the lower magnitude weights and try to see if eliminating them would actually impact the accuracy of the model. And there, what they're trying to do is essentially using the weights and their magnitude directly to prune the model. Here in this paper, they talk about how activations might be a better measure of the significance of weights. So they try an empirical study where they try to use just the magnitude of weights to determine the quantization scales, as well as a magnitude of activations to determine quantization scales. And they find that if you use activation scales, you see much better performance. So here is an interesting observations from this paper is that they say only 1% or even 0.5% of the weights within the distribution can contribute to a significant amount of accuracy degradation. That means if you have like in complete weight matrix of a trained LLM, if you're able to retain only the 0.5% of the weights in float precision, you can recover most of the lost accuracy from quantization. So, but retaining them in float precision is still a challenge. That means if you're doing the rest of the compute in integer and want to do just a few of these computes on float, you still need to have a very powerful float compute machine. Instead, what they suggest is, as we discussed with the basic quantization techniques, they're talking about the trade-off between scale and range. So whenever they identify this 0.5% of weights, they try to adjust the scale to accommodate for minimizing the quantization noise. So they are essentially identifying these salient weights that are less than 0.1% and trying to adjust the scale to account for precision and without adding much quantization noise. So this way, based on, again, even for this, since you need activation, you need a small calibration data set, which will allow you to understand the effect of weights on the activations. And based on the activation ranges, they're actually seeing which weights are more sensitive and which weights need more bits or scaled accordingly. So
do you support variable bits per weight because of the activation aware? Go ahead and repeat the question.
Sure. Yeah. So the question is about, do we actually support variable bits within the same weight? So this is what they're actively trying to avoid. So they actually use same bit precision, but once they understand that some of the weights are more sensitive, this is where the trade-off between scale, when we are trying to quantize a float distribution, we talked about how scale and offset determine the trade-off between precision and range. Yes.
Needed.
Yes. So they talk about, they identify these more sensitive weights and try to get the precision right for those weight. So they're not necessarily using higher bit precision because it takes a toll on the performance, but they're essentially modifying the quantization parameters to minimize the quantization error. So this is a way to identify the sensitive weights and use techniques to minimize quantization error for the suit. The first impression, yes, the way they evaluate this algorithm is through mixed precision. So they use floating point FP16, for example, for the salient weights. But it's when it comes to actual practical deployment, it's not really useful because even if you're trying to do a few arithmetics on floating point, you still need the accelerator to have support for float as well as int math, which will essentially increase the cost and area and etc. for the model. So more cost-effective or performant solution is to see if we can tune the quantization parameters to minimize noise. So the bit precision is still the same, but they are varying the quantization parameters to minimize the quantization noise.
You got the distribution to where the sensitivity is.
Yes. Adapt the, yeah, exactly. Adapt the distribution to where the sensitivity is. Yeah.
Can you expect what kind of application have you used to study these methodologies?
Yes. Yeah. 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 So for the most part, again, that's for the evaluation. We use wiki text as a basic metric. Again, these are not as widely evaluated because again, as I was mentioning, just evaluating LLMs is a topic in itself. What we're trying to do is take a bare minimum performance metric and see how these are able to satisfy that metric. This is very similar to what they do in CNNs, which are much well understood. Most of the optimization techniques are evaluating image classification on ImageNet. While the idea is if it's able to transfer and learn with ImageNet and do a good job, it should be able to learn other tasks in a similar fashion, might be able to learn and do a better job there as well. So it's you're right. This is again a study needs to be done in terms of like how quantitation affects the performance and metrics at a large scale. But for the study or the paper on AWQ, what they talk about is use some basic perplexity measurements and throughput measurements and apply all these techniques on various OPT, Llama, and Mistral kind of open source models to see how well this technique works. So it's more like they're trying to prove that this works and leave the more broader analysis of adaptation and accuracy measurement to the users.
When you have a large enough data set or diverse enough data set to know when to zoom in and do the pooling and the balancing of weights, etc.
Yeah.
Is that saying so? So maybe those domains were not there.
Yes, that's a really good question. So the question is about we are talking a lot about the calibration data set, getting the activation ranges, but if we have calibrated to a specific use case or specific data, will it generalize well enough for the other data sets, or do we need to collect enough data set of our interest to be able to apply this method? So that's I think where the design aspect comes into picture. This is where it leaves it open, and that's one of the reasons they simplify it and use much simpler like a wiki or a standardized data set to understand the applications of the algorithm. But as someone worked with calibration a lot, I can say that whenever I'm preparing a calibration data set, I try to make sure that to the best of my knowledge, I incorporate whatever use cases that I expect to see in my application. So, for example, not an example for LLMs, but for CNN, for example, if I'm working with images and if I'm expected to see both indoor and outdoor images, it is definitely problematic if you just calibrate on indoor images. You need to make sure that the calibration data set has both indoor and outdoor images to make sure that the quantized model lives up to its performance expectation. So it's up to the user to understand this calibration data set and apply this. So the only variability here is the calibration data set that the user provides, and they need to make sure that it is good for their application. Yeah.
What is the attention in that chart?
Oh, yes. So continuing with the slides. So in case of oh, yeah, the question was about in the slide we see attention and FFN and what are they about? So here what they're trying to show is how much of a footprint the weights as well as activations have. That means how much of the weights from the attention mechanism that we have seen in the multi-head attention in the transformer, how much footprint or the model size. So in terms of footprint, it's like if the whole model size is 60 GB, how much of it is coming from the multi-head attention and how much of it is coming from the fully connected feed-forward layer. So this is just an example that shows that the attention mechanism has contributes the weights from the attention mechanism contribute much more compared to activations. So this is their way of justifying using higher bit precision for activation. So if you see, they have 4-bit for weight and 16-bit for activation. And the essentially the thought process behind it is since weight contribute to a large portion of the overall network footprint or the memory size, by reducing it to 4-bit, you get much better advantage. You are essentially addressing the memory bottleneck challenges. Whereas activations, you can still keep them in 16-bit precision because their contribution to the overall memory bandwidth or the model size is not that significant. Again, it's essentially a trade-off. If you could, you would want to do the activations in 4-bit as well, but this is the kind of trade-off you need to do.
That's still the question. Ask what does it mean by memory footprint?
Oh, memory footprint in the sense what's the model size? So you have to store that model somewhere to load and run it on the device. So in this case, that's an example. Like if you take Llama 2, which is like 7 billion parameters and might be of size like 7.5 GB, how much of it is actually from the multi-head attention weights, and how much of the model size is coming from the feed-forward portion?
You're might be running it on small, less GPU RAM.
That's a good comment.
Yes. So again, when you're running it on edge devices, which are essentially limited in memory, the memory footprint is a significant concern. You either try to fit the whole model, or you try to move the necessary weights in and out of this edge device. What it means is you're either have to deal with smaller models, or if you have a larger model, you can't fit it into device, which means you have to deal with the extra penalty of the memory bandwidth that you have to load and unload these weights and activations for the execution. Yep. So again, yeah, here is an example on the perplexity metrics with both 3-bit and 4-bit compute, and using grouped quantization. And again, 8-bit and 4-bit are quite popular quantization techniques because most of the accelerators these days are able to support them, and that's what gives you the most compute efficiency. Now,
What would the abbreviation name, N3G28?
yes, so it is using integer 4-bit quantization for the weights, and using groups, as we discussed, like grouped quantization. So the group size is 128. Yes. So we talked about SmoothQuant, we talked about AWQ. Essentially, these are quantization techniques that help you mitigate the loss in accuracy when you're doing quantization. Another popular technique for LLM implementation is Llama.cpp, which is essentially a pure C++ implementation. It started off as a project that they wanted to run C++ implementation of LLMs. And since most of the people are interested in efficiency, it made sense to implement it in C++. And it is kind of growing really well, and we see a lot of quantization schemes covering from like sub 2-bit to 8-bit integer quantization schemes. And we're going to go into details of how this implementation works. So while it is very similar, I think it's important to understand the distinction. So it also has 2 types of quantization, also called type 0 or type 1. When we compare it to the traditional quantization, this might be compared with symmetric and asymmetric. And as you can see, they calculate the quantized weights from the floating point values using the min and offset. So in this case, a clear distinction is the M, which is the offset. When in the traditional quantization, we use integers for offset. Here they are using float. I think this is a very clear implementation choice that they have made to have better performance. And so that's about quantization types. And when it comes to quantization mixes, this is about how the whole transformer model is quantized. Like we have seen in the past, we were using softmax or the matmul or fully connected layers were quantized for integer precision, whereas the other memory bond operations were running in float precision. In this case, they have multiple integer precision. So they have 4-bit precision for the compute intense operations, and for activations and others where they deem necessary, they have higher bit precisions like 5-bit or 6-bit. And they have been able to achieve good performance with this approach. So again, I think the recurring theme is you have mixed precision implementation and you allocate these bits wherever necessary, either with the weights or the activations. So
Just based on your experience, you have better luck trading off precision by only quantizing latter layers, or you guys are quantizing the entire model? Because I assume that as you go into the earlier layers, you'll be giving up too much precision.
So I think based on my experience with CNNs, I can say that the initial and the last few layers tend to contribute much more in terms of quantization noise compared to the intermediate layers. Again, this is with a caveat saying that whenever we see quantization failure, more often than not, it can be attributed to a few layers. So I've not seen in like 4 or 5 years of me working with quantized models, I've not seen a case where it kind of grows, the quantization grows along the depth. It's more like a random noise. That means if you try to plot the quantization error across the network, it is more randomly distributed. And if the model is failing quantization, it's probably because 1 or 2 layers in them are not probably supported fully or deviating a lot. And once the information is lost, the next layers can't recover it. So it's either that or yeah. So does that answer your question?
Yes, so your experience with your start from the latter quantized, and did you still have it to go one layer down and you progressively go through it, or you attack it all at once and then sort of do arbitration work backward? Just from an infinite.
So the question is whether we tackle one layer, the initial layers, the following layers. So essentially a more progressive approach to quantization, or we take the whole network as a whole and quantize the whole thing and see if it works. So the more popular approach has been the later, that is, we take the whole model, try to quantize it, and if it doesn't work, then we have some tools that help us identify, again, as I said, what are the problematic layers and see if we have to do mixed precision on that. Like, so if we have identified maybe some softmax is causing the problem, then instead of quantizing it, we'll keep it in float and try to delegate it to CPU and see if it recovers the accuracy. And if it does that, then that's probably how the execution works. So very rarely, because very rarely I've seen an incremental approach with layer to layer, because we don't have enough understanding of the intermediate representation to make sense of whether it's a good quantization. So we rather take the whole model as a whole and quantize it and measure the end-to-end metrics and see if it works or not and see what we can improve on it.
And do you guys do some proprietary profiling tools to understand that, or?
It's not necessary. I mean, again, coming from the CNN background, there are quite a lot of quantization analysis tools that even TF Lite offers. For example, they give you an analysis of layer-wise quantization error. So what they do is, again, this might be a digression from the topic. So Sure. But there are a lot of publicly available tools that will help you with the quantization analysis.
Thank you.
Yes. So yeah, coming back to Llama.cpp implementation, what they do is essentially, again, we are trying to do matmul or fully connected. They divide the whole tensor into smaller blocks and they compute these quantization parameters for each block. And what it does is essentially we are making a trade-off, in the sense, if you have a too small block size, you are essentially, you get better precision, but your the overhead of quantization kills the performance. So you might have to make the right trade-off between performance and precision. And once we have this block quantized input tensors, we use more efficient matmulls on these block quantized blocks. And again, having hardware support, they can be run on 4-bit or 8-bit to get better compute efficiency. Now, here's a typical example where you have a 4-bit quantization and you're essentially dividing, for example, a 256 block, and you have the overhead of saving the float, the offset or the scale in float point. What it means is that while you are using 4-bit for most of the weights, because of the overheads related to offset and scale, you essentially end up getting like more like 4.5-bit precision. So if you in the quantization scheme you are seeing some fractional bit support, that's probably because of the overhead that we see from this block quantization. And here is an example of the perplexity as well as performance on Llama.cpp. As you can see, they have a wide range of quantization schemes from 2-bit to 6-bit and FP16. And popular schemes tend to be more around 4-bit because many of the accelerator do support them out of the box. And then they're able to achieve 1 to 2%, 1 to 3% accuracy deviation. And similarly, a significant jump in the performance. So, yeah. And
If you don't mind,
sure.
can you say, in segment tell us how many
Oh, wait. Okay, that's a good point. So here, if you look at these, there are different quantization schemes. 2, 3, 4, 5, 6 essentially stand for number of bits they are used to represent the weight. A catch here is that they're not purely 4-bit or 8-bit quantization. So like we have seen in the previous case where we were using 4-bit for weight, 16-bit for activations, and FP16 for some of the other operations, it's essentially a mixed precision implementation. Similarly, in this case, when they say Q4K, it means mostly 4-bit. What that means is some of the activations where they fit necessary, they use 6-bit quantization schemes so that they can accommodate for the extra precision needed. So in this case, Q40 represents, as we have discussed, type 0 and type 1. So 4-bit symmetric, so to speak, distribution. Q41 example talks about 4-bit asymmetric quantization. Q4KS is S stands for small. What that means is they try to use 4-bit for most of the layers and maybe 5-bit or 6-bit for the sum of the activations. So that's what makes it small. Whereas 4KM stands for medium. So what it means is they use 4-bit whenever convenient and use 5 and 6-bit for more activations and more. So what it means is that the model size will be larger for 4KM than 4KS when compared to 4K0. So 4K0 will have the smallest model size, 4K1 will have a little larger, 4KS will have much larger, and 4KM will have a much larger size. So it's essentially they're trying out different recipes to see what works best. And yeah, again, these are 4 variants for 4-bit. If you go to sub 4-bit, there are much more variants.
I think the point is that U6K model, but the model size almost half the original was 128 gigabyte compared to 52, but the accuracy is only 0.16% different. So we have a very accurate model, but
Yeah, you're talking about the
yes,
yes, yes, yes, yes,
so we always keep the same accuracy,
yes,
but with a much smaller model.
yes. That's correct. So yeah,
Thank you.
this
so yeah,
describe your differences?
yes.
But first to make some favors for well, this but I've never been implemented. And it felt like Llama.cpp plus Llama.cpp, like, we have no idea what we are doing, but we implemented it, it seems to work.
Not really. Most of these methods. So the question was about, we discussed three quantization schemes, and the first two seem like uh, more like theory, and we don't have a proper implementation. Whereas Llama.cpp looks like a more implementation is done, but the theory or the practical approach, the theory behind is not well established. So actually, all these three methods are quite popular in terms of quantitation schemes as well as implementation. So if you go back and search AWQ, SmoothQuant, you will have a PyTorch implementation for that for sure. And you should be able to, that's one of the reasons I'm able to show some of the results, because they do have these implemented. And these are some of the popular techniques in the industry. And when it comes to Llama.cpp, it is more in it's more of a practical implementation that is more than the algorithm. The novelty of Llama.cpp is that it is a bare bones C++ implementation. So they actually implemented something from scratch. So if you look at the block quantization, it's not necessarily like groundbreaking, so to speak, but the fact that they have like no dependencies and have implemented it from scratch in C++, that's what makes it a very attractive option for people who want to run LLM inference with a like efficient LLM inference.
Yes, it's. Remember, once we you putting experiments with multi-model models or the LLMs, there's no language model. Those are also quantized together when they align basically images of text.
So the question is about have I worked with multimodal or vision LLMs, and how does the quantization affect their performance? I worked a lot with the traditional vision models like CNN, but I haven't worked much on the vision LLMs, so to speak. So I can't really comment on what kind of performance impact quantization has for those models. But again, this is where I'm trying to keep it like more generic, in the sense these are model weights. We're talking about model weights. We're not talking about text input or vision. I have seen this applied to vision models, CNN models, and work as well as we are showing it right now. So I don't see any reason why it would not apply. So at the end of the day, again, they are trained models with weights and activation. So yeah, I think it should. I think most of the key takeaways should still be applicable, but I don't have like empirical data to support that.
So to say, from 2019 to 22, my team was doing a lot of quantization on vision models, the current things that were embedded in the paperclip code. And so a lot of times we cut the models to half the size or a third the size. And we had a threshold, we didn't want to get below 1.5% accuracy drop. So that's what was common in that year range.
I just want to elaborate where my question's coming from. So I see that the NVIDIA released a large visual model. The Llama is a generic, right? And they have their own version of Llama, I believe. They released it in May, so 2 months ago. And they also released quantized versions for edge devices, aka Jetsons. That's one we just tried to what the accuracy. And there was this now.
I don't know about the accuracy for that, but it's a lot easier to evaluate the accuracy for vision models. Because if you have bounding box around them, it's pretty clear. Or if you're classifying it into noun X versus noun Y. So it's a lot easier to evaluate the accuracy of vision models than the LLMs tends to be a little bit fuzzy.
Yeah. So yeah, even my experience, I've worked with CNN models. Most of the principles about quantization have been applicable to those models as well. But again, I believe it also depends on this particular task. For example, if you're talking about classification or segmentation, they are essentially decision making kind of operations, which might be more robust to quantization noise when compared to like if you're trying to do a pose estimation where you're doing a regression on the vision models, which might be more sensitive to quantization noise. That's essentially the takeaway. But again, so yeah, again, thanks for all the questions. So essentially, we kind of try to summarize the importance of quantization and try to understand fundamentals of quantization and what kind of trade-offs it involves and the challenges and how these techniques tackle those challenges. And we kind of did a deep dive into some of the popular post-training quantization schemes like SmoothQuant, activation-aware quantization, and Llama.cpp. Uh, I had a last slide on questions, but yeah, feel free to ask any questions here. Yes.
I just pulling out for a bit of a bigger picture question about where else has analogous research occurred in the last few decades like this? I mean, like some folks say on the outside of this field, just looking at the results, they're kind of stunning. How many bits you can drop and still get great results. How widespread the impact is because these smaller models aren't merely saving a few bucks, but they change the footprint drastically to be able to run on device, to run on the phone, to run in the field. It's just been such an exciting problem, but I'm also a little bit worried as to like, is this somewhere on the hype curve between a really great old set of techniques in the toolbox applied to a very exciting new area? Or are there ways which is generally new? So it's going to be pulled back and said, where are the analogies to other kinds of research? You know, are these cases where maybe in the past these were like well known in the area of rendering and graphics and kind of how we did adaptive meshing and so on in 3D CAD? Or, you know, is this generally saying it's a new area because we're only beginning to enter the place where we can start doing co-design hardware and software and start seeing chips that are built from the ground up and varying solutions that we're starting to see in this new wave of GPUs. So kind of how new is this approach and what are the analogs to it in the context of computing history?
Yeah, I think the question is about, again, it is really interesting to see the results of quantization and how the kind of savings that we see. Is it really new or are there existing techniques in some other field that can be applied here? Again, while I can't talk about a broader, like the rendering or graphics part of it, based on my experience from vision and CNN models that I've worked with, CNN models are much well understood than LLMs. So there are quantization techniques, quantization analysis tools. As I was talking about, like TF Lite has these quantization analysis tools. Again, they feel like I think CNNs seem like much well understood compared to LLMs, which means if you look at CNNs and optimizing them for edge, you will see knowledge distillation or pruning or quantization or network architecture search with added hardware awareness to it. So you see a lot of research in those areas, as well as how the loss space and how, I mean, even the evolution gives you a good idea of how these models have evolved. Like, I think there is a popular example of the loss space with and without skip connection that shows that how variable the local minima is. That means even a small change in quantization can pull you away from the minima, which might break all the KPIs that you have. And many of the CNN tools like Popular TF Lite, what they offer is once you know that the quantization is off or you are seeing more drop, like more 5% drop, or which is more than what is accepted. I think the industry standard is 1 or 2%. It should be within 1 or 2%. If it drops more than that, there are techniques like mixed precision or layer-wise analysis tools or more techniques like weight equalization, which is kind of very similar to the SmoothQuant that we have seen to recover those. So again, this is me talking about my experience working with CNNs. And I do feel that CNNs have like, been with us for a while, so they're well understood. And I think we can expect similar trends or approaches for LLMs as well. even with accelerators, if you see, there have been a lot of accelerators that have been designed for CNNs. Now they're trying to run transformers on them and not doing a great job on it. So eventually we'll probably have more transformer-centric accelerators, which might be able to do a better job and understand transformers also better, similar to CNNs. Yeah, I think this is where I feel the research that is done on CNNs can definitely be applied to LLMs. And part of what I'm doing is that I'm taking my experience working with quantization of CNN models and looking at LLMs and see how I can leverage them.
Well, thank you. That's how unprecedented this is. I certainly haven't seen it as in crypto or bioinformatics or else. This playbook being applied from CNNs and LLMs. Very exciting.
This is something I just want to know. At the NVIDIA GTC conference, in Jensen Huang's keynote, he was quoting NVIDIA's latest B200 next generation GPUs in terms of how many flops it can perform, and he was quoting the number of 4-bit floating point flops. What is a 4-bit floating point? What does that mean?
Yes. Yeah. So yeah, I think yeah, I think the way we are looking at numbers have changed, and I think they are being adapted to how the deep learning networks work. So I think the most standard was the IEEE 785 standard for floating point. That was like reigning for the most part, and now we have more data variants that are more hardware friendly, and so that's why we see FP8, BP16, and FP4. So essentially, again, it's yeah, exactly. So the sine, mantissa, and exponent, and they just change the way how many bits are allocated for mantissa. Those details I'm not sure, but something like that.
Okay.
So,
I guess, sorry, one other one, I just see these things, I don't understand them, so, I played with, Llama.cpp 1-bit. And I was baffled by what that would, is that the weights? What does that 1-bit quantization mean?
Yes, yeah, essentially, as we have seen with Llama.cpp or other techniques, it's essentially how many bits that you are using to represent the weights. And this is like
Are the activations larger floating?
yes, that should be. I mean, that's what I would expect. This is the same with even CNNs. We have like binary or tertiary networks that are like essentially 0, 1s, or 2-bit weights, and there are, I mean, research that shows that they work, but they're not as well and widely adopted as 4-bit or 8-bit, because many of the existing processors can support 8-bit, and they have like nice techniques, engineering techniques that they do to convert these 8-bit operations to 4-bit by packing in the bits in within the 8-bit. So that's one of the reasons I would say the 4-bit, 8-bit are still popular because of the inherent support. But in terms of research, yes, they are like 1-bit, 2-bit.
So they have a question about a different approach. Instead of quantization, isn't that possible to start training the model with the limited resources we have on the edge devices? So like start the model from the scratch and do the quantization.
So you're talking about on-device training?
I mean, from doing this quantization on vision models in the past, trying to train constrained hardware would just give you models that don't function. It would just work much better to train on much broader, richer models, larger word size, and then quantize. So I haven't tried that on LLMs, but that was experience on vision models from 2019 to 22.
The way I see it is quantization is like a fine tuning. So you train it on larger hardware and whatnot, and quantization essentially is more like a fine-tuning technique that you have a limited budget and compute and memory, so you're fine-tuning it and trying to see if it can retain its learnings.
And then the passing, a little bit of training,
Yes,
to have a recover.
yes, yes.
So how does it, when you talk about the error rates, how does it manifest itself? Because if you have a 1% error rate or a 10% error rate, is it just the language is a lot funkier? It's, it's not as elegant when it, like, the result of the text that it generates, the, how does it manifest itself? What do you see as the error rate gets worse?
I mean, I've seen it. I'm not sure how. Okay, the question is how. Yeah,
JPEG, going back to something simple, but that's also a quantization thing.
Yeah.
As you crank up the compression, start to see the blocks, and it gets less and less, detail within those blocks, and then it gets very blocky. But the artifacts become more and more obvious visually. So if this is LLM, I assume you're talking about text. Then is it going to be like in English, you have a lot of synonyms, you have a lot of ways to say the same thing. Is it come across a little funkier or a little, like, what is the, how does it,
Yeah.
He's asking in a
Yeah, yeah.
practical way.
in a practical way,
The
what's the
error-
end result?
The error we see, how does that show? Like the text is generated is not as good, the image, like what happens when there is an error?
Like the perplexity changes.
Yeah.
You
So
notice.
the question is about how the error, for example, the degradation 1% or 2%, how is it actually seen in the output? And I think at least in terms of like 1% or 2% drops, I think it's really hard for a human evaluator to actually judge. But I've seen cases where it kind of failed drastically, and those are not even English characters. It just tries to print some, because I think the decoder, the tokenizers and the decoder that is trying to decode kind of gives you out some kind of gibberish. So it could be like letters, but don't make any sense. It's just as if like you're typing, banging on the keyboard or something like that. Yeah, but there are cases where I think in most of these papers you can actually see that they talk about prompting them and seeing the response, and the better the perplexity metric, the better or coherent the answer is for a human reader. Like you can actually think that okay, this answer makes sense.
I wasn't sure if it was like using the wrong words or spelling errors or if it was hallucinations.
I'm not quite sure about that, but I think it's a mix of everything, because if you read it, I think you can tell, but I'm not sure how to classify. Yeah. My question? Yes.
We use to remove
I beg your pardon. I couldn't hear your question. Can someone repeat?
training, quantization, we use to remove
I don't know.
quantization
So the question is, what is the post-training quantization technique used by Google?
by training.
Well, no, it's, post-training is different.
Yes, I know, but weren't you asking about learning training?
No, post-training is after training.
Training. You're asking about, I thought I heard you say training. Well, you mentioned the Llama or Meta, but I'm sure Google has something equivalent.
I'm not sure about that. What Google is using here. These are more like widely accepted. There are much more. I mean, these are just most widely known popular techniques. There are way too many to be able to cover in a talk about it. Yes, sorry. Yeah.
In the presentation, you mentioned that we are not doing. And I was wondering maybe based on the experience of that two questions very long. With your experience, how much more expensive you quantization aware training given to and are you aware of any LLM this was trained quantization aware?
So the question is, in regards to quantization aware training, am I aware of any LLM model that was trained with QAT.
First purpose. Is it significantly more expensive to use these?
So the first answer is I'm not sure. Like I haven't seen an LLM model that is advertised as QAT, but I did see some models. I think there is a startup called Desi. I'm not sure if you have heard of it. They I think NVIDIA recently acquired it. So they used to do a lot of quantitation friendly models. They were a startup that is kind of a cutting edge on deploying NAS for hardware awareness and things like that. And I do remember they had certain LLMs for code llama kind of models that they claimed that they were more quantitation friendly and much smaller in size. So that's the best I'm aware of in terms of QAT. In terms of cost associated with QAT, um, I've seen that again, this has multiple factors. I think QAT in terms of as a tool itself is it's not well developed or optimized. So what that means is I've seen models that without QAT, which might train in a couple of hours, might take like a couple of days if we enable QAT. So it could be, it's not just because the amount of compute that comes with QAT, but how it comes along with the whole framework as well. So when you are having these QAT nodes, how does it work? How efficiently you are able to train it, and how these additional nodes, quantize and dequantize node, affect the overall training performance as an
It also impact RAM. Training RAM.
yes, yeah. Yeah. So yeah, thanks a lot for all the questions, and I'll be here if you have any other questions for the next 10 minutes again. Thanks.
Folks, remember, you're here at Hacker Dojo. It is a nonprofit and basically fulfilled by means of its members and people who come and volunteer to do things like teach classes and things. So I urge everyone to look into joining Hacker Dojo as a member. Thank you.